Hi students, welcome to Mosaic Academy UTME lesson series. Now you are welcome to the topic of thermometry, thermal expansions and calorimetry. So under this, we are going to be looking at 10 questions as usual. So like I do say, time is a major constraint. We need to up our pace so that we can finish up and focus on some other things which is still need to know. Because physics is very wide. We still have chemistry and the math challenge to also focus to. So like I said, this was the first series will be all topic. So I start with the first one. If you find anything interesting, don't forget to like and subscribe the channel. We start with the first question. The first question says, 5 grams of ice at 0 degrees Celsius is dropped into a beaker containing 20 grams of water at 40 degrees Celsius. The final temperature of the piece is slash. Now, to solve for final temperature, I hope you have studied the concept of calorimetry. About that, we have a situation about conservation of heat according to joules. Heat can be converted to work and therefore work can also be converted to heat. So if you need to work concepts, search on this channel. They are available as many as you want up to the highest of the highest level. Now, about this, we have the mass of the water, cold water, and hot water. Let's just take heat loss by cold water is gained by hot water. We'll just heat loss by hot water as temperature loses heat loss by hot water is equals to the heat gain by cold water. So the basic concept of this from junior classes is heat loss is always written as MC theta. Remember, this is mass of hot water is equals to MC theta. This is mass of cold water. So on simplification, we can cancel C out because they are equal. Specific heat are equal in this case. So mass of hot water was the mass of hot water. If I go by this 20 grams of water at 40, you can see the temperature is 40 here. So that is 20. That is why I'm looking for that. Into bracket, the temperature change of hot water, the final temperature of hot water is 40 minus the final temperature of the mixture. Let's say theta 3, which is what we are looking for, as x must always be equals to the mass of cold water is 5 grams. I'll just say 5. So the temperature of cold water is 0. So we say the final temperature of the mixture is x minus 0. I've done this on my channel. It's available there. You can always watch the concept. So let me cut. 5 can cut. Here 1, here 4. So on distribution, I'm going to have 4 times 40. 160 minus 4x is equals to x minus 0 is x. Move this to the right hand side. I'm going to have 160 is equals to 5x. On simplification, x, which is the final temperature, is 160 divided by 5, which is nothing but 32 degrees Celsius because I'm working Celsius, I didn't convert to Kelvin. I hope you understand that MC theta 2 minus theta 3 is equals to MC theta 3 minus theta 1. That is the concept we focus on there. That is topic is calorimetry, the aspect of physics that deals with what heat exchanges. The second question about this, the resistance of the resistance thermometer. That's another type of thermometer. This is on thermometry, I think, has values of 2.71 and 3.70 ohms at 10 degrees Celsius and 100 degrees Celsius. The temperature at which the resistance is 3.26 is that you can use your isometer calibration you have studied in your junior classes, and as well, you can just use a simple understanding. Let me just help you with the two. If you deem to understand, look at it. The initial resistance thermometer has the resistance is what 3.17 and 2.71 at this temperature and this. So now, if I go for the temperature difference, for example, at 90 degrees Celsius, how did I come about 90 degrees Celsius? I subtracted 100 minus 10. That is the change in temperature as what the value of the resistances will also be 3.70 minus 2.71. 3.70 minus 2.71 should be 0.99, if I'm not mistaken. So at 90 degrees Celsius, its rate is 0.99 ohms. I'm just looking using like chemistry relationship. Now, if the resistance of the temperature at which the resistance, what's temperature, let's say X temperature, we now read when the difference is now, you can see when the resistance is now 3.26 ohms. So 3.26 minus 2.71. So the temperature at 90 was the difference between these. What will be the temperature when the difference between this and the initial temperature? That's 3.26 minus 2.71. I think that is 0.55. So how do we do that? You just cross multiply. So on cross multiplication, you can say x will be 90 times 0.55 divided by 0.99. I think should be able to do this. And this is 0.10, and this is 55. Okay, this is 50. Please confirm 50 degrees 50 degrees Celsius. You can always confirm. It's always good to confirm. Just punch your calculator because of time. I'm not going to be confirming all this stuff, but you can always do that because it's important to confirm. I can't make, it's very hard for me to make mistake, but sometimes if there's a mistake, you can always drop down the comments at the comment section. So this is that, and that is the correct answer to that. So the next one, let's be fast. That's the second question. We still have a long way to go. I don't want to be wasting your time. I want to be using 30 to 33 minutes. The thermometer whose reading is indicated by the color change in thermometric property. Thermometric properties are properties of what? Of a liquid that changes with changes in temperature. Some thermometer, you cannot measure the rise and fall of temperature directly. You need to measure their thermometric properties, and there are different types of thermometer you have studied in your junior classes. A very good example of them is the first option, the bimetallic stripe, is talking about two similar metals, changes in two similar metals. Thermocouple is talking about resistances. You measure resistances to get the measurement of temperature. Watch my concept on thermometry. You are going to get that. Platinum thermometer has no resistance. You can see the one we saw now. Just in what the change in resistance of the thermometer will give us the change in temperature. Then the last one, optical pyrometer, is a special type of thermometer that is used to measure what when we have a solid substance. For those of you who are here to watch concept video, as I'm taking you along with all these simple concepts, you can always record my voice, download it, and also watch and over and over again. This measures the temperature of a solid substance, high temperature of a solid substance at the point of color change. That is the point at which it is always being marked. So it indicates a color change when the temperature is high. And at that point, we say what we are measuring thermometric property because we are measuring the temperature. So those whose readings indicated by change in color is called optical pyrometer. So you can always see that at the back of the line. So the next question about this dear student, a square plate of size 10 centimeter is made of a metal of linear expansivity of 2.2 times 10 raised to power negative 5. Please note that this is raised to power negative 5 per Kelvin. The SI unit of expansivity is per Kelvin. As the plate is heated from 30 to 100, the area of one face of the plate will increase by that. I think this is one of the famous topics you all like in your junior classes. Now, area, you can say the area, the new area, I call it area, final area is equal to initial area, open bracket, 1 plus beta change in temperature. I'll just write it like that. Whereby beta is called coefficient of what? Of superficial expansion, which we call area expansion. Is the same thing. It's given as 2 times the linear expansivity. From the linear expansion, there's 2 times 10 to the power of negative 5. On simplification, 2 to the 4 times 10 to the power of negative 5. So, like I said, I will always leave it for you. Then you need to get the initial area. It is a square plate. The importance of a square area of square is always L square. Another important thing is the answers are in centimeter. So I may not convert here. So directly I can say this is 10 square. That's 10 to the power of 2. Everybody knows 10 square is 100 centimeters square. So initial area is 100. We finish this. We open a bracket. 1 plus beta, we just change from what linear to what superficial to area. So that is 4 times 10 to the power 5 or negative 5 multiplied by change in temperature is always final temperature minus initial temperature. So change in temperature is just like 100 minus 30, which is 70. So on simplification, you get the answer to this. Like I do say, drop your answer in do the one in bracket first, like multiply this with this, It's very simple to multiply. I can help you. So this 220 can say that's 2.20 can set to minus 4 plus 1 and multiply by 100. So that is the word. You say multiply by 10 raised to power 2. So that you can also reduce the 10 raised to power whatever. So that's I think it's 1 over 1.4. I'm not sure. You just put your answer in the comment section. This is very simple and it falls under thermal expansion. The next question for today, question 5. About question 5, we are also solving question on thermometry, which is conversion of scales of temperature. There are 5 basic scales of temperature conversion, but for your level, you were taught only 3, which is not that bad. So you might have studied how to convert from degrees Celsius to Fahrenheit. Now, the way we convert is we just use the isometer rule, which I said is common in junior classes. We say the temperature 45 minus, I'm in degrees Celsius, the highest point of degrees Celsius is 0 over the same point of degree Celsius is 32 minus the highest point must be equals we are going to Fahrenheit. So let's say the temperature in Fahrenheit is X minus the highest point in Fahrenheit is I think the highest point is the highest point in Celsius is not 32. The highest point in Celsius is 100. So please permit me. Then this is the highest point in Fahrenheit is 32 over the same point is 212 minus 32. So on simplification, we have 45 over 100. I think this method is old school. I don't even like it. It's x minus 32 over 212 minus this will be 180. You can simplify and get your x. Some people will say then you get your x as whatever. Put the answer in comment. But look at the direct way. You can also do this without wasting time. I'll give you the direct way. This is to convert to degree Fahrenheit is always 5 over 9 times degree Celsius plus 32. This is always better. Short is better in examination. So 5 over 9 times degree Celsius. We are converting 45 degrees Celsius. We are adding our answers to 32. 9 here 1, 9 here 5. As 5 times 9 are 45. 5 5s are 25. 25 plus 32 is nothing but 57. So this is 57 degrees Fahrenheit, which I think is the correct answer. If we break this thing down, we are going to have the same answer. Yeah, I can say 0 gets cancelled out. My way of solving, 5 zeros are 9, 5 zeros are 2. So on simplification, this is going to give me 9 times 18. My word, my word, my word. Still giving me wow. Okay, 2 here, 1, 2 here, 9. I can always cut. That's one thing about me. I think 2 here, 1, 2 here, 9. As 2 times 9 are 18. So if we go by that, I can now say 9 times 9 are 81. I hope I did not screw this. 81 as I cross multiply is equal to x minus 32. Wow. Then 81 plus 32 is equal to x. 113 is equal to x. Yes, actually this is correct. And 113 also, and they should be the same. So let me see where I screw it here. Oh, I've seen my mistake. The formula is not 5 over 9. The formula is 9 by 5. So it's 9 over 5, my dear student. I'm sorry about that. Thank God I used this method. I would have screwed the question. So let's just change it to 9 by 5 and solve. You are going to see that the answers are going to be the same. Sorry about that. It happens sometimes, and that's why I like confirmation and verification. I don't practice questions. If our questions are being brought by the team, most the academic team student, I always compare question. So I just want to provide solution. So doing this, guys, 9 by 5, we're multiplying this by the degree Celsius we have is 45, then plus 32. You can see that the answer is correct now. 5 here 1, 5 here 9. As 9 times 9 is going to be 81. 81 plus 32 is going to be 113. So guys, apologies for making that mistakes. So mistake they say don't have what mass. So now the next one is a piece of iron of mass 100 gram and specific capacity of 460 kilogram per Kelvin is cooled from 70 to 20. So the release of heat, this is also under tab the calorimetry. Now, quantity of heat, basic question is MC change in theta, the way you guys write it, theta T. So now, or theta 2 minus theta 1, anyhow. I'm not going to convert anything except I'm going to convert this one, but this is in kilogram per Kelvin. So this is going to give me mass is 0.1. You can ask me, I have divided this by 1000 and I move on with red ink. Specific heat capacity is 460 according to the question, multiplied by the change in temperature is final temperature to what? To initial temperature. This is 70 minus 20, and that is going to be 50. On simplification, this is 2.3 times 10 to the power 3 joules. So which I think because this is being typed, and that is why it is mostly academic property, we are typing it. That is why it is like this. So I think that's the correct answer. This is a simple question which I believe everybody should be able to do. On to the next one. Sorry guys, apology, I have to rush you. It's because of time, and time is always a major constraint when we are dealing with stuff like this. We have to finish up everything as promised. Now, this says that a mass of 0.5 kilogram of water, we have a mass, we have a temperature, is converted into ice. When it was converted, there is a change in what? Temperature. Very good. Now, the specific capacity of water is 4.2 kilojoule. Is it kilojoule or joule per kilogram per calorie? I don't know. I think it's a typo. Maybe it's kilojoule. I just take it as kilojoule per kilogram per calorie degrees Celsius. And the specific latent heat is also, this is also in kilojoule, 334 kJ. Amount of heat extracted. Now, we've talked about quantity of heat when there is a change in temperature, which we call specific heat, MC, change in temperature. We also have quantity of heat when there is no change in temperature. That can take place in two processes. When ice is converted to what? When ice is cooled from solid to liquid, or when what? It is also converted from liquid to what? Vapor. Call it latent heat of fusion and latent heat of vaporization. So in this case, look at it. This was first of all cooled. Then after it has been cooled, there is what? You can see cooling out is a mass was what was converted into ice. Water was converted to ice of 0 degrees Celsius. So the first thing is the temperature is going to be changing. For example, I'm saying here is specific from 10 degrees Celsius. The temperature was cooled down to 0 degrees Celsius. And after it was cooled down, you know, this is hot water, it was cooled down, there's a change in temperature of specific heat. So later, 0 degrees Celsius, latent heat now, was now converted to what? 0 degrees Celsius, which there is no change in temperature. So what I'm saying is that the total amount of heat that is what carried out during this process is a combination of two types of heat exchanges. The one with a change in temperature and the one without a change in temperature we call ML. L can be latent heat of fusion, but here it is from solid to liquid. So please note that. So now by that, my dear student, we can just substitute parameter. I think this is simple. Some people like to factorize, but if you don't want to factorize, do not change anything. It's 0.5 multiplied by, I'm working in kilojoule 42. Change in temperature is 10 minus 0, that is 10. I'm adding that to what? The same 0.5. Latent heat of fusion in 3 kilojoules is 334. I'm not going to finish this as usual. You multiply everything and you tell me the answer in the comment section. The methodology is what you need now because we are almost there where we are going. On to the next question. The next question here is the same quantity of heat which raises the temperature of a certain volume of water by 10 degrees Celsius also raises equal volume. That's equal quantity of the Q is same, V is also same. But the temperature differences are what? For water is 10 and for oil is 20. The relative density of oil was 0.75. So the ratio of the specific capacity of oil to that of water is dash. Well, I think this is also very simple, just relationship wise. We say the quantity of heat is always equal to MC change in temperature. So if we make the relationship of mass subject of formula, because the same quantity was passed, this is constant. I can say mass is equal to Q over C into bracket theta 2 minus theta 1. The relationship I want to make here is just for us to understand the certain process. So we can say the mass is inversely proportional to specific heat and temperature. That is, the higher the mass of the substance, the lower the specific capacity of that substance. So by the way, I can just relate this directly. As you know that density rho is equal to mass by volume. The volume is said to be constant. We can say as density increases, the mass also what increases according to the question. So I can say that in terms of density, which is relative density here, I can say they have a direct relationship with mass. So now, since mass is inverse, we have to change the specific of temperature. So we have to just inverse our relationship of temperature. So what I'm saying is that the one of oil over the one of water, will now be equal to, we have to inverse the specific capacity of oil to that of water. I will say C of oil over C of water will now be equal to temperature of water. My dear student, what is temperature of water? Over, we have to just reverse over temperature of the strength by 20. That is 1 over 2. You write as 1 ratio 2. I hope students understand. And if you don't understand, watch my full concept. This is very fast for you to know all these properties and formulas because I'm going to tell you a lot of details. So we move to the last section, I guess. Wow, I think this is the last section, question 9 and question 10. Hope I'm not rushing you guys too much. 25 minutes, 30 minutes is always our target. So the next question says, I think this is also on time. Okay, this is also calorimetry. A cold water tap supply water at, you can see cold water supply water at 20 and hot water tap at 80. To obtain a warm water, cold water plus hot water will give you a lukewarm water. Second law of thermodynamics. We talk about the entropy, chemistry students. Entropy. Now, the question is the ratio of the mass of cold water to that of hot water. We did something like this in the previous slide. We said MC theta heat loss by hot water is the one gained by cold water. So if I go by simplification here, I can say the simplification of this is nothing but, let's see, it will be, so it will be, like I was saying, it will be MC theta equals to MC theta. So from there, we can just say directly, we need to know that this is for the hot water and this is for the cold water. Let's just substitute values more or less like what we did the other time. So substitution with the mass of hot water, I just like temperature as usual. See, I said we get cancelled out. Temperature change in hot water. We did that before, 80 minus 40, theta 2 minus theta 3. That is that. Is equals to, we have mass of cold water, theta 3 minus theta 1. Theta 3 is 40, theta 1 is 20. So just like what we did. So MH times 40 as 80 minus 40 is 40 is equals to MC times 20. So we are looking for mass of cold water to cold water. That is MC over MH. And that will give us nothing but 40 over 20. And that is what 2 over 1, which is 2 ratio 1. So that's the answer to that. And for the last question of today, guys, apologies, guys, for the break in transmission. So we have a tire is pumped to a pressure of 30 Newton per meter at this temperature. When the tire is heated up to this, the new pressure is assuming there is no change in volume. From your gas law, this is, I think this is also more like gas law, PV equals to NRT. So NR are constant, also here V is also constant, but NR is always equals to PV by T. So that is so if V is constant, you have P by T, that's P1 by T1 is equals to P2 by T2, which I believe you have talked about as pressure on the junior classes. So just substitute value as the first pressure is 30 and volumetric fluid over the first temperature is 300. How did I come about 300? You guys know. This is I added 273, I converted to thermodynamic state is equals to the new pressure is P2, then 273 plus 54. I just want you to see the process so that it won't be as if I'm doing stuff that you did not know. This is 7 plus 5 is 12. This is 327. 327. So I think year 1, year 10, we don't need to waste time. So when you cross multiply, you are going to see that P2 will be equal to 32.7 Newton per meter squared will be the question this time. And that is the answer to the question. Guys, that is the end of today's section. I'm going to see you tomorrow by the grace of God for the next section and the next topic. Then we are going to also talk about, I think tomorrow's topic should be more like heat transfers and rate of flow of heat. So, and some questions on paper. So see you guys soon. Do have a wonderful time and don't forget to subscribe and like our content. Thank you. Nothing.